Okay, think about this for a second. How exactly did artificial intelligence go from barely being able to string together a coherent paragraph just a few years ago to suddenly writing entire novels, generating complex code, and literally passing bar exams? What actually happened? Well, it wasn't just, throwing more data at the problem or building faster computer chips. It was actually a singular, massive architectural breakthrough. So our goal in this explainer today is to lift the hood on that exact engine, the transformer, and completely demystify how it works. And the best part, we're going to do it entirely without math.
All right, let's dive right in. Here is our roadmap for this explainer. First, we'll look at the sequential problem. Then, the 2017 breakthrough. Next, we'll use the cocktail party metaphor to explain how it works, followed by parallelization and massive scale. And finally, we'll wrap up with statistics, not genuine understanding. By the end of this, you are going to have a really clear, intuitive grasp of the single most important innovation that basically made this entire current era of AI possible.
So starting with part one, the sequential problem. To really appreciate this massive solution, we kind of have to look at the roadblock that had AI researchers completely stuck for about 2 decades. We need to talk about the bottlenecks of what's called a recurrent neural network, or an RNN.
Before the transformer came along, RNNs processed language sequentially. It was a very strict step-by-step process. Step 1, read a word. Step 2, update the internal state. Step 3, read the next word, and so on. Honestly, it was a lot like trying to read a book with one eye closed while pointing at just one word at a time. And the fundamental flaw here is that in a sequential processor, distance dilutes meaning. If you have a pronoun at the very end of a sentence that refers back to a noun 50 words earlier, that connection is super weak. Why? Because the network's internal state has already been overwritten dozens of times by then.
Think about how we read. While humans do read sequentially, we have working memory, we have common sense, and we can instantly jump our eyes back and forth across a page if we need to. But an RNN reading a long text, it experienced something more akin to you walking into a room and completely forgetting why you went in there in the first place. By the time it reached the end of a long passage, it had totally forgotten the beginning. Now, researchers did try to fix this with some clever architectural patches, things they called LSTMs and GRUs, to try and give RNNs selective memory. But at the end of the day, they were just bandages. They didn't actually fix the core issue of sequential processing.
Which brings us to part 2, the 2017 breakthrough. Look, by 2016, the entire field of AI was basically stuck. Everyone knew models needed to process much longer contexts, and everyone knew that sequential processing was the bottleneck holding them back. But that all changed in June of 2017. Get this, a team of 8 researchers at Google Brain published a paper with this aggressively modest title, "Attention is all you need." And the crazy thing is, they weren't even trying to revolutionize the entire AI industry. They were just trying to solve a very specific machine translation problem. Yet in just 12 short pages, they introduced the transformer architecture to the world. And the impact of that 12-page document, it literally cannot be overstated. It has been cited over 100,000 times since then. By any measure, it is one of the single most influential technical papers in the entire history of computer science. It essentially birthed the modern era of the massive models we use today, like GPT-5, Claude 4, and Gemini 3. Moving on to part 3, the cocktail party metaphor. So how does this revolutionary architecture actually work? Well, the central insight here is best understood not through a bunch of complex equations, but through a really relatable everyday human experience. The core mechanism powering all of this is called self-attention. Imagine you're at a super crowded cocktail party. There are dozens of conversations happening all around you. Now, you aren't processing the room as a strict sequence of isolated sounds, one right after another, right? If someone 3 meters away suddenly says your name, boom, your attention shifts instantly. Your brain is processing that room as a web of relationships, basically attending to the whole scene at once. Well, self-attention does something incredibly analogous to that. Instead of reading left to right, the transformer looks at every single word simultaneously and asks, hey, which other words in this sentence are the most relevant to understanding this specific one? Because as we know, context is absolutely everything. Take a simple word like bank. Just looking at a dictionary can't tell you which of these 5 totally different meanings applies in a given sentence. Only the surrounding context can do that. For an old sequential machine, resolving that kind of ambiguity was incredibly hard. But self-attention? It solves this instantly by allowing the AI to draw direct connections. If the word bank is sitting near the word river, the mechanism instantly highlights river as highly relevant. The model can see the relationship directly, no matter how many other words separate them.
Let's look at a really simple example of this in action. The cat sat on the mat because it was tired. When the transformer processes that word it, the self-attention mechanism looks at every single other word in the sentence and assigns it a relevant score. Cat gets a very high score. Matt gets a super low score because, well, mats don't get tired. It actually computes these scores for every word in relation to every other word, creating this massive relational map. And because of this, distance no longer destroys meaning. The connection between it and cat is computed directly and instantly.
Okay, part 4, parallelization and massive scale. So the cocktail party metaphor beautifully explains how self-attention actually understands language better, but there is a whole second half to this story. We really have to pivot to the hidden revolution here, parallelization. This right here is why transformers practically took over the world. With that old sequential processing, word number 5 couldn't even be processed until word number 4 was completely done. That meant training these models took agonizing months, even on the absolute fastest hardware available. But self-attention, it's parallelizable. Because it computes the relationships between all words simultaneously, you can split all of that work across thousands of processors at the exact same time. Better architecture plus exponentially faster training allowed researchers to scale up wildly. And this sheer, massive scalability, it unlocked something honestly incredible. Emergent capabilities. Look at the progression. At 1 million parameters, the AI could do some basic text completion. Ramp that up to 1 billion, and suddenly you get really coherent paragraphs. But when parallelization allowed researchers to train models with 100 billion parameters or more, the models suddenly began exhibiting sustained conversation, complex coding, and logical reasoning, behaviors that look astonishingly like real human intelligence.
Which brings us to part 5, statistics, not genuine understanding. And this is perhaps our most crucial section, because these emergent capabilities look so incredibly much like human intelligence, it is wildly tempting to just treat the transformer as a kind of magic. But we really need a sober reality check here. The absolute essence of what is actually happening under the hood is simply this. The coherence is very real, but the understanding is not. The AI has zero model of the physical world. It has literally never touched a cat, and it has never sat on a mat. When it writes a flawless, completely convincing essay on quantum mechanics, it isn't understanding physics at all. It is simply predicting which words are statistically likely to follow each other, based on trillions of examples it's seen before.
Think about the fundamental difference here. True human comprehension is founded on actual physical world experience, which results in real semantic knowledge. You actually know what a cat feels like. The transformer, however, is built purely on word embeddings, which are just mathematical representations of text. Its output is just highly advanced statistical pattern matching. It can give you medical advice without understanding a drop of medicine, and legal analysis without understanding the law. It's an elegant, absolutely brilliant statistical map, but trusting its magic blindly, that's a dangerous trap.
Now look, the AI field evolves weekly at this point. Since 2017, we have seen massive innovations. Things like mixture of experts, state space models for even longer contexts, multimodal processing for images and video, and complex alignment techniques to shape behavior. But while the specific technologies change at lightning speed, the enduring foundation remains exactly the same. The core insight of the transformer, that parallel, relationship-aware processing of language, completely beats sequential processing. That is the undisputed bedrock of this entire technological era. Knowing the difference between statistical patterns and real understanding is absolutely the key to using these systems wisely. So as we wrap up this explainer, I really want to leave you with this to consider. When you interact with today's AI, when you trust it with your research or your writing, are you relying on its statistical brilliance, or are you mistakenly expecting genuine comprehension? Just keep that in mind the next time a chatbot gives you a perfectly written, heavily confident answer.